If it works. Okay. So we talk a lot about titration curves. The reason to talk about titration curves is the titration curve is a picture that represents what happens to the pH as you change the mole ratio of your weak acid. Okay. I hope this is working. Okay, so as we titrate, what is happening to the number of moles we have of our starting acid and its conjugate base? So at the very beginning point, we only have HA, right? At the equivalence point, we only have the conjugate base. Halfway in between, what do we have? Be bold, speak it out. So what we're doing over the titration is gradually moving the reaction farther and farther to the right. So if we're only halfway to the end point, we've moved half of the starting material to product, right? Which means we have the same amount of starting material as we have of product. Okay, if we are here, what do we have more of? Our acid or the conjugate base? Acid. Okay, if we're here, what do we have more of? More conjugate base than the acid. So one way to think about a titration curve is that it's actually demonstrating what happens to the pH as you change the relative amounts of the HA to the A-. Does that make sense? When we have no HA and all A-, you're at the equivalence point. At the beginning, we have only HA. But as we move through the titration curve, we're gradually increasing the amount of conjugate base and decreasing the amount of the starting acid. Mole ratio. Okay, so can we conclude? We're talking about a weak acid. The pH of the solution depends on the relative amounts of the weak acid and its conjugate base. If you mix them in different quantities, like if you were just to make a solution with different quantities of a weak acid and its conjugate base together in the same solution, would you get different pHs depending on what mole ratio you use of the different things? If I make a solution that has a bunch of weak acid and even more of the conjugate base of that weak acid, on a titration curve somewhere above the midpoint, right? Hold that thought. Okay. If we go back to this curve, the titration curve has a different, relatively flat region at a different pH for every acid, right? And the flat region roughly centers around the pK of the acid. Is that true? Yeah. Okay. There are a ton of applications where we need a solution, an aqueous solution, to keep its pH relatively constant. And the truth is that doesn't happen for just a solution sitting on the benchtop. So for example, water, an aqueous solution will absorb a small amount of carbon dioxide from the air, which is converted to carbonic acid, and that changes the pH. Or if you're mixing solutions, sometimes you end up with different pHs. And there's lots of scientific applications where you need the pH to be exactly where you want it. Because if it's not, it ruins your experiment. For example, proteins, a solution of a protein will only stay folded within a fairly narrow pH range. So if you're trying to do biochemistry or biology and you're working with proteins and you can't keep the pH of your solution constant, the protein will unfold and your entire experiment will crash. How important is it to keep the pH constant? Absolutely important. Okay, here's some other examples. Analytical chemists do a series of experiments, chromatography, where you separate things in a mixture based on how they interact with whatever you're studying. If the pH isn't right, what happens to those experiments? You're done. So it's really important that you be able to control the pH. Well, one way to control the pH of the solution is to take advantage of what we know about the titration and say, okay, if I have a specific acid with a specific pKa value or a specific Ka value, if I mix that acid into solution with a whole bunch of its conjugate base, I can set the pH of that solution to be about where the pKa is. If I have a one-to-one solution, one-to-one amounts of the conjugate acid and the weak acid, then my solution pH will be exactly the pKa. If I need it a little bit higher, what do I do then? Add a little bit more of the conjugate base. So the fact that the titration curve works the way it does means that chemists have a lot of flexibility to set the pH exactly where we need it to be and to keep it there. Okay, so a solution that has a weak acid and its conjugate base together in solution at the same time in order to set the pH at a certain level is called a buffer. And all of biology and medicine needs buffered solutions. So for example, if you're a patient in the hospital and you're seriously dehydrated and they need to give you an IV solution of water, they can't just give you water intravenously because the water is not the same pH as your blood is. And you would dysregulate your blood pH if they just added water. What would the impact of that be? Would it be death? If it's bad enough, like if it's enough of a pH dysregulation. So the IV solutions that they give people are actually a buffer solution that contains, it's usually a phosphate buffer solution. I think that would be at the right pH. So the point is, we use these buffers all the time and in lots of applications where you didn't even know that they use it. Okay, Thanksgiving is coming. Those nice juicy turkeys that you buy that have been injected with a solution to keep them juicy. What do they inject them with? Buffer. Yeah. Okay. So if we have a 1-to-1 ratio, that gives us the buffer with a pH, which is perfect. But sometimes you need it to be a little higher. You need the pH to be a little higher or a little lower. If I need the pH to be right here, what if I need to be slightly higher than the pK? What am I going to do? Just add more of the conjugate base, right? And if I need the pH to be a little bit lower than the pK, well, I would just add more of the acid. Okay. Yes.
Can you buffer with bases and their conjugate acids?
The same thing. Yeah, as long as it's a weak acid conjugate base pair, it's the same. Let's do okay. So it's a weak acid and its conjugate base in significant quantities. Doesn't have to be a 1-to-1 mole ratio, but it has to be, they have to be within 10-fold concentrations of each other. Okay. Then you get a pH and you can calculate it with this beautiful equation. What's the name of it? Henderson-Hasselbalch equation. How do you remember the equation, by the way? I mean, you'll have it on this sheet. So Dr. Rebecca Sansom expressed it as pH equals pKa plus log AHA. AHA. She said that sounds way better than log HA. So the conjugate base is in the numerator and the weak acid is in the denominator. Okay, so this equation. This equation actually isn't new. Have you figured out that nearly every time we show you a new equation, it's really just a rearrangement of something you already knew? This is no exception. If I take the equilibrium expression, and this is expressed in terms of Arrhenius, but we could have done it with Bronsted-Lowry as well. So we want the equation to be pH equals something, right? So we're gonna take that H plus and put it on one side of the reaction of the equation. Can you see that this is just a rearrangement of the same thing? We divided both sides by the proton concentration. Okay, now take the log of both sides. If you take the log of both sides and simplify, you actually end up with the Henderson-Hasselbalch equation. So this equation is just a rearrangement of the Ka expression. It does assume that the equilibrium concentration of acid is indistinguishable from the initial concentration. And that is true for nearly all of the weak acids, right? Because usually we get to neglect X in the denominator. So really, this is just an easy way of calculating the pH without a rice table. Okay, so we use the Henderson-Hasselbalch equation because we want to make a buffered solution and we need to know what concentrations of weak acid and now suppose I need a buffer that's buffered to about pH 6. pH to be 6. I'm standing in the lab. How do I make a buffer solution at pH 6? What do I need? The first thing that I need is a weak acid that has a pK of about 6. So I go to the shelf and I look at all of the weak acids and I say, which one has a pK of about 6? And I'll pick one. Okay, and then I have to make up a solution that has significant quantities of the weak acid and its conjugate base. Can I do it with a strong base? Strong acid? This only works because you need a situation where both the weak acid and its conjugate base are fairly reactive. They both have to be capable of reacting with stuff. So you can't use a strong acid because its conjugate base won't be reactive enough. We usually have the pKs of about 3 to 9. That's just sort of standard weak acid range. Okay, if you need the pH of the solution to be exactly the pK of the acid, then you use a 1-to-1 ratio of the conjugate of the weak acid and its conjugate base. If you need the pH to be a little higher, what does the equation say? Equation, we'll talk about this. If you need that, there's 2 ways to think about this. One is using the math and one is just conceptually. If I want the pH to be higher than the pKa of the acid, I need it to be a little more basic, right? So what do? Add more of the conjugate base. If I need the solution to be a little more acidic than the pK would be, then what do? Add a little more of the weak acid. Yeah. Okay, 2 ways to do this. One is to carefully measure out exactly the right amounts of the weak acid and the conjugate base that you need. Make the right mole ratio and hope that when you make your buffer, it's perfect. In practice, Josh, does anyone actually do that? You actually do.
What's this there?
Okay, if we go back to our titration curve, could you start with all of the conjugate base or all of the weak acid and just titrate till we got to the right pH? When you did that, you will have converted the solution to the right relative concentration. Okay. I love that picture of a baby because it looks like my nephew. My nephew's now 7, but in my head, he's always going to be about that age. So. Okay, so the Henderson-Hasselbalch equation is just an easy way to work equilibrium problems when you have a weak acid and its conjugate base. That's all. It's a super easy way to do it. There's 2 ways we do it that we're going to do in recitation. One of them is I say, okay, if I make a solution that has this conjugate base concentration and this acid concentration, what will the pH be? You just plug it into the equation. Or I could say, I want a solution of this pH. What ratio of that weak acid? So let's do an example. Okay, so I have a solution, 0.3 molar in ammonia and 0.2 molar in ammonium chloride. What's your clue that this is a buffer solution? First of all, there are two things present. If you look at the Ka table, ammonium is the acidic form and ammonia is the conjugate base. So when you're working a problem like this, make sure you know what you have. This is a buffer solution. Okay, so our buffer pair is ammonium, that's the acid, ammonia, that's the base. We know what our Ka is because we can look it up on the pKa table. So we know what our acid concentration is, we know what our base concentration is, we can calculate the pKa, it's 9.24. Okay, how do I solve for the solution pH then? Let's plug it into the equation. Okay, so you say the pH is pH of 9.24 plus log of ammonia concentration divided by the ammonium concentration. Question marks in that. Okay. You have some intuition to help you catch any mistakes that you made. So first question, is the pH approximately what we would expect? So we expect the pH to be about around the pKa, right? So the pKa is 9.24. We calculate a pKa that's a little higher than that. Is that what we should have? What do we have more of, the acidic form or the basic form of the buffer pair? We have more of the basic form. So is this pH what we should expect? Absolutely. Okay. What if we needed to make a pH, a solution of pH 9.42? The Henderson-Hasselbalch equation could show you how to do that. Okay, how do we make it? First, we have to look around to find the appropriate buffer pair that has a pH, has a pKa around 9.42. And when we look on the table, guess what? We're going to choose ammonium and ammonia. Because ammonium has a pKa of 9.24, pretty close to 9.4. Close enough anyway. Right? Okay. We have chosen a different buffer pair. Yeah, we could have. Okay. So the real question is, what's the ratio of ammonia to ammonium? Now notice something. The Henderson-Hasselbalch equation is expressed in terms of concentration ratio, right? The equation is expressed in terms of concentration. Is the ratio necessarily the concentration ratio? If we take moles per liter and divide by moles per liter, do we have to have the liters in there? Both of the weak acid and the conjugate base are in the same volume of solution, which means that the concentration ratios in the equation are identical to the mole ratios. Okay. So what ratio would we need to get solution pH? How would we approach that? Tell your neighbor how you would do that.
Basically just want to isolate the AHA part. So,
Yeah, we just want to solve. Ben says in the front, you want to solve for the AHA part. Right? You do. So you rearrange the equation. You get pH minus the pK equals the log of what you want to solve for. How do you get something outside from inside the log function? The base 10 log, so you have to do 10 to everything else. So the ratio you get is 10 to the exponent of the pH minus the pKa. Okay. So we use that to solve, and we get the ammonia to ammonium ratio is 1.51. What does that mean in actual terms? What does that mean? If we solve for a ratio of 1.51, what does it mean? It means one of them is in 1.5-fold excess. Which one is in excess? top is, so that means you have 50% more of the conjugate base than the acid. So if your acid concentration was 100 millimolar, what would your conjugate base concentration be? 150 millimolar. You need 1.5 times as much ammonia as ammonia in your solution. Now, what kinds of concentrations do buffers typically have? What's the common buffer concentration? Are we talking like 3 molar? What are we talking? They're usually millimolar. So typically 10 millimolar, 50 millimolar, 100 millimolar, relatively dilute. Okay. Read the equation for what it tells you. Okay, tell your neighbor how the equation says this. If you take the base 10 logarithm of the number 1, what do you get? 0.
I knew you meant.
So when the removal ratio or the concentration ratio is 1, the same amounts, what do you get? Yeah, pH equals the pK. Is that what the titration curve told you?
Mhm.
Yeah, that's what the titration curve says. Okay, how about this one? When you dilute your buffer, what happens to the mole ratio? What happens to the AHA ratio? It stays the same. So that's helpful. And in fact, in the lab, people do this all the time. If you need a buffer that needs to stay at a certain pH, you could spend half of your time in the lab making buffers, for real. So this is what people do. They make a concentrated solution of buffer, like 10 times the concentration that you need. But we call it a 10x buffer. You can store it in a jar. When you need to make more buffer, then you just dilute it tenfold and you're good to go. And the reason you can do that is because once you pH or set the pH of your concentrated buffer, then the pH is going to stay the same every time you dilute it. Very helpful. Okay, tell your neighbor why this statement is true given the equation. Okay, so if you have less of the conjugate base than the acid, that ratio is less than 1, right? What's the base 10? What do you know about a base 10 logarithm of a number less than 1? Negative value. So if your AHA ratio is less than 1, your pH, pK minus a number, so your pH is lower. Okay. Now I have on this slide the corollary, adding strong acid to a buffer will decrease the pH slightly. If we add strong acid to the buffer solution, what happens to the ratio? Come back to that, but what happens if you happen to add some strong acid to it? The strong acid will react with the conjugate base, convert it to the acidic form of the buffer pair, change the ratio. Okay, tell your neighbor why number 4 is right, based on the equation. Why does the Henderson-Hasselbalch equation say in math that statement?
That's adding it to something. That's just like a number.
So when you add, when you have more of a conjugate base in the weak acid, your ratio is more than 1, right? When your ratio is more than 1, what's the sign of a base 10 log of that number? It's positive. So you're adding a positive number to the pKa, so your pH is higher than. Okay. Finally, see if you can connect this to what you know about pH. If you change the ratio of weak acid to conjugate base, if it's tenfold, It's gonna make the pH go up by 1. How come? So if the AHA ratio is 10, what's the second term in that equation? Yeah, if you take the base 10 log of 10, you get 1. And so if you change that ratio by 10-fold, you're 10-fold higher or 10-fold lower, the pH will change by 1. Okay, think about conceptually what's happening here. Let's do this. Spend some time working through this. Move a little faster. Always the problem. Okay, let me just point out some things that are valuable here. One of the reasons that a buffer is so important in how it works is that what we've done is made sure that in solution, we have a stronger acid than water and a stronger base than water. Remember all those reactions and solutions that we've done where the acid or the base is going to react with water, right? And when it reacts with water, it produces either hydroxide or hydronium, right? When we produce hydroxide or hydronium, what happens to the pH? Changes dramatically, right? Okay, when we put a buffer pair into the solution, what we're adding is a decoy. Anything that's acidic or basic will react with the buffer instead of with water. Okay, so the solution, the buffer, contains both a weak acid and a fairly reactive conjugate base. So anytime we add or happen to have something that's acidic or basic that mixes with the buffer, it's not going to react with water, it's going to react with the buffer instead. Okay, but when it reacts with the buffer, if you have a base and it reacts with the buffer, it's just produced a little bit more. Does that have a big effect on the pH? You're just kind of slightly moving it along the titration curve. Okay. So if you add any acid, then the acid will react not with the water to produce hydronium. Instead, the acid that you add will react with the buffer base to produce the weak acid form of the buffer. Okay, so essentially the buffer is there to trap added acid or base. Why is that important? When you do reactions or biological experiments, there's lots of things where something's an acid or a base that gets mixed into the solution, and it would cause the solution pH to fluctuate wildly with resultant disaster for your experiment. But if you put the buffer in there instead, you keep that from happening. Okay. So, here's my order here. We'll come back to those. We're not just skipping them. I changed the order this morning and now I like my old order better. Okay, so why does it matter that you have a buffer? Let's just contrast how a buffered solution behaves versus how a non-buffered solution behaves. So first thing, dilution. If I have 10 milliliters at pH 2, if I dilute those 10 milliliters 100-fold to 1 liter, what happens to the pH? Okay. So just answer it conceptually. I know what my hydronium concentration is, right? I can calculate it from the pH. What is it? 0.01 molar. when we dilute our hydronium concentration, if we go from 10 milliliters to 1 liter, we're diluting 100-fold, right? So when we dilute our hydronium concentration, what happens to the concentration? It goes down 100-fold. When the hydronium concentration goes down 100-fold, what happens to the pH? It goes up by 2 pH units. And the one pH unit corresponds to a 10-fold change in hydronium. Okay, so every time you dilute 10-fold, your hydronium concentration is going to change 10-fold. So we would go from pH 2 to pH 4. Okay, we could also use math to answer that. We could say your initial hydronium concentration from the pH is 10 to the minus 2 or 0.01 molar. And we did that by taking the hydronium concentration equals 10 to the minus pH. Okay. When you dilute it, you can do a dilution calculation. You're diluting 0.001 molar, pH 4. Okay, so does dilution make a huge difference to a non-buffered solution? Absolutely. Okay, what about when we do it for a buffered solution? So the Henderson-Hasselbalch equation, when you dilute the solution, what happens to the ratio? Nothing. So what happens to the pH when you dilute a buffered solution? Nothing. So instead of going up 2 pH units, pH doesn't change at all. Is that useful? Yeah. Okay. Suppose we're doing an experiment where you need to add a certain amount of acid. Like maybe one of the reagents is only soluble at low pH. So you have an acidic solution that you need to add to the rest of your solution. If your original solution is not buffered, if you add 0.01 moles of HCl to a liter of water, what's going to happen to the pH? Go down because you added HCl, right? How much is it going to go down? It went from pH 7. So the water was pH 7, right? And we added HCl, we create a 0.01 molar solution. What's the pH of an 0.01 molar solution? 2. So how many pH units did it go down? 5 pH units, which corresponds to a change in hydronium concentration of 10 to the 5th. Is that a big difference? Yeah, absolutely. Okay, what if we have a buffered solution? When we add our HCl, what's that HCl going to do? Will it react with water? So up here, the HCl reacts with water to produce a whole bunch of hydronium, which is why the pH changes so much, right? But when we add the HCl to a buffered solution, what is the buffer? What happened? What's the reaction? The acid is going to react with the strongest base present. Is it water anymore? No, it's the conjugate base of the buffer pair. So when the added acid reacts with the conjugate base of the buffer pair, what does it create? It makes more of the acidic form of the buffer. How much effect does that have on the pH? Not very much. I'll show you that one. Well, we're going to do that in a minute. Okay, so when we add acid to water, it reacts with water to produce a whole bunch of hydronium. When we add acid to a buffer pair, what does the acid react with? The conjugate base of the buffer pair. What's the product? Conjugate acid of the buffer pair. So all we've done is mess with our AHA ratio a little bit. How much effect does that have on the pH? Just a little. Essentially, what we're doing is taking that added acid and converting it to more of the acidic form of the buffer pair, which is a weak acid. So we just took our strong acid and funneled it into a weak acid, so it doesn't have very much effect. Okay, let's do it for adding a strong base. If we add 0.01 moles of sodium hydroxide to a liter of water, our hydroxide concentration goes up. Our pOH is 2, so our pH is 12. So again, we changed our hydronium concentration by 10 to the 5th by doing this one. Okay. If we add the strong base to a buffer, what will the base react with? Is it gonna react with water? Well, because there's another stronger acid than water present, which is the acidic component of your buffer. And what will the product be? It will be the basic form of your buffer. So what did you do? You just changed your AHA ratio a little bit. So is that gonna have a big effect on your pH? No, it's not. Okay, now I'll go back to how do we calculate what the impact is? Okay, there is a new, like a rice table, but it's not a rice table, called a BCA table. Okay, and what you have to consider is if you're adding strong acid or strong base to a buffer, the reaction of the acid or base is with the buffer. So what you're doing is changing your relative amounts of your buffer pair. You're changing the AHA ratio. And your BSA table, or BCA table, just helps you keep track of what's happening. Okay, rice tables, we use molar concentrations. BCA table, it's really just a way of tracking a titration of your weak acid. I'm getting looks like whatever. You have to know how to do this for the exam this week. Screw your courage to the sticking place. Okay, so if we're adding base, strong base, to our buffer pair, in the buffer pair, I have HA, my acidic component, and my A minus, my basic component. Now the base that you add is going to react with your acidic component to create more of your basic component, right? So let's just track the concentrations, number of moles of everything we have before the reaction happens. So we just calculate how many moles we have of our starting acid. How many moles we have of our buffer base component. How many moles we add, and then track what's going to happen over the reaction. So let's do an example. Okay, so we start with a buffer that has a bucket load of buffer components in it, 1 molar. That's kind of unusual, but it makes the point. If I start with half a liter of my buffer, what's the pH of that buffer? And then you could just use the Henderson-Hasselbalch, right? So the pKa, the acetic acid and acetate, the pKa of acetic acid is 4.74. And we can calculate the pH of the buffer just by taking the relative quantities of acetic acid and acetate. Now here's a question. This ratio here says 0.5 over 0.5. But the formula uses molar concentrations, and the molar concentrations are 1.00. Is it a mistake that it says 0.5? Somebody explain.
Together.
You can use the mole ratio interchangeably with the concentration ratio here. And if I have half a liter of a 1 mole per liter solution, I have half a mole of each of the weak acid and conjugate base. So in the math here, I've just put in the moles instead of the concentration, which works fine. The reason that I did that is because we're going to, when we do our BCA table, to calculate what happens to the pH of the buffer when we add base to it. That's base. We need the number of moles. Okay, so now we add 0.01 moles of sodium hydroxide. What is the sodium hydroxide going to do? Normally, sodium hydroxide would dissociate, right? But now we have a buffer acid present, so what's it going to do? React with the acid. So we write the reaction. Acetic acid plus hydroxide goes to water plus acid. Okay. Now set up your BCA table. The B stands for before the reaction, the change in the reaction, and after the reaction. Okay, so if I have 0.5 moles of acetic acid and 0.01 moles of hydroxide, put that back to your stoichiometry days, do we have an excess reagent and a limiting reagent here? Yeah. What's our limiting reagent? Hydroxide is our limiting reagent. So all of the hydroxide is going to react so that we use up that amount of hydroxide. It's going to react with that amount of acetic acid to produce that amount of the conjugate base. Okay, so we can use that table to calculate what the new amounts of our buffer and our conjugate base, our buffer acid and our conjugate base should be. What should happen to the pH? We just created more of the base than the acid in the buffer, so our pH should go up slightly. And it does. We go from 4.74 to 4.7. Okay. Is that a big difference? When we added 0.01 moles of sodium hydroxide to water without the buffer, what happened to the pH? It went up 5 units. When the buffer's present, what does it do? Not much. Keeps the pH relatively stable. Okay. Can we do it in the opposite direction? What if we added acid instead? That case, we already calculated the pH of the buffers, 4.74. What we did before. Okay. Now we add 1 moles of HCl instead of sodium hydroxide. What will the HCl do? What will it react with? It's going to react with the conjugate base with the acetate. So we write the reaction. Hydrochloric acid will react with acetate. Acetate was hydrochloric acid, acetate is the base, right? It abstracts the proton from HCl to form chloride and acetic acid. We set up our BCA table. These numbers. Oh, in this case, now I just have 250 milliliters instead of half of 500 milliliters. Okay, so if I have a different volume of the same concentration, I'm going to have different numbers of moles, right? If I had 0.5 moles of each of my buffer components before, if I start with half as much, I'm going to have half as many moles. So I have 0.250 moles. I still have 0.01 moles of HCl. HCl is my limiting reagent. Acetate is my excess reagent. So I'm going to use up enough of the acetate to react completely with the HCl that I added, which will produce a certain amount of chloride and acetic acid. And then I can calculate 0.250 minus 0.01 equals my final concentrations of acetate. I can do the same thing for acetic acid. Okay, now can I calculate my pH? Yeah, plug it into the Henderson-Hasselbalch equation with the new amounts of my buffer components, and I get pH is 4.71. So, relatively straightforward. You just have to track what's happening. Okay. Let me move forward and look through loose acid so that we get through it. Then practice this, come to recitation if you're having problems with how to do the problems. So take home message, a buffer. When you have a buffer system present in solution, you have a stronger acid than water and you have a stronger base than water. So any added acid or base can be trapped by reacting with the buffer components and not react with water. And because what the buffer does then is just change its ratio of weak acid to weak base, the pH doesn't change very much. Whereas anything that reacts with water as the acid or base, you get a lot of hydroxide or hydronium. It has a huge effect on the pH. We need the pH to stay relatively constant for pretty much everything science does that involves a solution. So we use that. There's this idea called buffer range that the textbook talks about. I will not ask you to calculate buffer range. The point is, the more buffer component, like the higher the concentration of buffer components in solution, the more added acid or base it can trap, right? if you do the BCA table, the pH shift that you get when you add acid or base depends on the concentration of the buffer components you start with. So the more of the buffer components you have, the greater your buffer. Let's see, buffer capacity, that's what I'm trying to talk about. Your buffer range. You really, the buffer pair that you choose can only, you can't keep the pH stable above about pH 1, higher or lower than that. Okay, let's do Lewis acid bases. Lewis acid base will become the foundation for what you do in organic chemistry. Here's the question. We talked about Arrhenius acid base theory, and we talked about Bronsted-Lowry acid base theory. Wouldn't it be nice if we had a theory of reactivity that covered a whole bunch of reactions instead of just proton transport? Do you remember Lewis from Lewis diagrams? You know Lewis's backstory? He really set out to revolutionize chemistry. He was actually nominated for the Nobel Prize 47 times. Did he ever win? No. And the reason that he never won is that the Nobel Prize Committee likes to give the Nobel Prize for one single discovery or one single paper. And the work that he did revolutionized the way scientists and chemists thought about reactions, but it wasn't a single breakthrough. So he never won the Nobel Prize. And there is, in fact, some question about whether he committed suicide. So he was kind of bitter about never being recognized for his contributions. And the day he died, he had lunch with a former colleague who was also a competitor, Langmuir, who had recently won a series of big awards. And one could imagine that Lewis wasn't very happy about that because, I mean, he invented Lewis diagrams. He came up with the definition of a covalent bond. We're going to talk about what he did for acid-base reactions, but he wasn't ever recognized the same way. He went back to his lab. Later that day, he was found on the floor of his lab dead. And he'd been doing experiments with hydrogen cyanide, which is a poisonous gas. And people said they could smell the hydrogen cyanide in the air. So there'd been some kind of leak. And he was not a scientist that you would have thought would have killed himself by accident with the hydrogen gas. Now the coroner ruled it a heart attack. So we don't really know what happened. But when you think about Lewis diagrams and Lewis acid base, think of Lewis changing the face of organic chemistry and not getting recognized. On my list of things to figure out in the next life, one that doesn't matter that I'm curious about is what really did happen to Lewis. Okay. So there's this category of what we call acid-base reactions that are Lewis acid-base reactions. Okay. And Lewis acid-base reactions describe Bronsted-Lowry acid-base reactions, but they also describe other kinds of reactions. Okay, put it in perspective. You're used to seeing an acid base as the base grabs a proton or the proton kind of hops off the acid and moves to the base, right? So your focus is on the proton, eyes on the proton, right? Lewis acid-base reactions say, no. When you track a reaction, you're tracking how the bonding changes, and the bonding comes from the electrons, right? So instead of looking at the protons, look at what's happening to the electrons. Okay. And in this case, the acid base, the acid is an electron pair acceptor. When something forms a new bond, it's accepting electrons to make a new bond. Okay. And base is an electron pair donor. Okay, in this case, let's look at, let's look at this one. what's happening? Starting with the rest of products. We're forming a bond. Lone pair form a bond, with proton, right? And that's how you form this covalent bond here. So can we say that water is donating electrons? Because here it owns the whole lone pair. And in the product, it's sharing the lone pair with the proton. In this case, water is an electron pair donor. What's the proton acting as? We could call the proton an electron pair acceptor because it's accepting the bond. Okay. Bronzed-Lowry acid base are actually a little more complicated version of Lewis acid base. So let's do an easy example of a Lewis acid base. In this reaction, we're going to form a bond between the nitrogen and the carbon, right? So can we say that the carbon is accepting the lone pair from the nitrogen? Because it's gaining a new bond, right? So that would make this molecule here an electron pair acceptor or a Lewis acid. And the lone pair on the nitrogen, what's happening to it? It's donating it to make a bond with. So the ammonia here is a electron pair donor or a Lewis base. The way that chemists track reactions like this is with what we call curved arrow notation. And in organic chemistry, you will use curved arrow notation forever and a day. It will become your language. So I'm introducing you to the curved arrow notation. So you're one up on all the other people who start 351 without ever seeing it. Okay. So the curved arrow notation starts with the Lewis base. You take the lone pair that's going to become a bond. And you draw the curved arrow starting with the lone pair that's going to become the bond. Point the arrow to the atom that it's going to make the bond to. So this arrow here means this lone pair becomes a bond to the carbon. Now this is a little more complicated because how many bonds can carbon form? Only 4. So here we have carbon with 4 bonds. If nitrogen makes a bond to carbon, that would be 5 bonds. So what has to happen? Break a bond. So the electrons that are in this carbon bromine bond, that bond breaks and the electrons go to the bromine or bromide. So what happens? The bond breaks. Okay. So anytime you see a curved arrow from a lone pair to an atom, that means a bond forms. And when you see a curved arrow starting with a bond and going to an atom, that means that bond breaks and the electrons from the bond become a lone pair on that atom. Okay, how do we recognize a Lewis base? A Lewis base is something that donates a lone pair into a bond, so it just has to have a lone pair. Can we say that every Bronsted-Lowry base is also a Lewis base? The only requirement for a Bronsted-Lewry base really is that they have a lone pair. So yeah, if it's a Bronsted-Lowry base, it's also a Lewis base. How about Lewis acids though? A Lewis acid is anything that can accept an electron. It can accept a bond or it wants more electrons. So easy examples. BH3 is open shell, that would be a Lewis acid. If we consider that a strong acid produces H+, according to the Arrhenius model, would H+ be considered a Lewis acid? It wants a bond. It wants some electrons. Yeah. Anything that is electron deficient or open shell is a Lewis acid. Okay. Can you take what you have previously seen as a Bronsted-Lowry acid-base reaction and describe it in terms of Lewis acid base? So think about what's happening here. We want to say the proton is donated to water, right? In Lewis acid base terms, what we say is a lone pair on oxygen makes a bond to the proton. So that the water is what? Lewis acid or Lewis base? It's the Lewis base, and this molecule is our Lewis acid. Okay, so a bond forms between the oxygen and the proton. The bond between the oxygen on the acid and the proton breaks. Okay, this is just proton transfer looked at from a different direction, right? Same thing. Okay, Bronsted-Lowry acid base is kind of a subset in the larger category of Lewis acid base reactions. But we can do Lewis acid base reactions that don't involve proton transfer. So let me erase the board. See if you can draw the arrows for water reacting with water. You already know what the product is for water plus water, right? Okay. It's helpful here, always draw in your lone pairs. You know what the products are going to be here? This is the autoionization of water. The equilibrium constant is the Kw. Okay. So what we know is we have to form a bond between the proton and the oxygen of water to form hydronium, right? Lewis acid base terms, the lone pair reaches out, forms a bond to the proton. How many bonds can hydrogen make? One. So if we form a bond, what do we have to do to this bond? We have to break it, and then electrons from that bond go to the oxygen to form hydroxide. That's all we have to do. Okay, how about this one? Ammonia. Yeah, great. Now in this case, in order to predict what you have to figure out what's going to be your Lewis base and what's going to be your Lewis acid. So what is your Lewis base? The Lewis base needs lone pairs. We only have one thing with lone pairs, right? So ammonia is going to be your Lewis base, which should make BF3 your Lewis acid. What does the Lewis acid have to have? It has to need a bond or be positively charged. Does BF3 have a full octet? That's open shell. Because if you draw the Lewis diagram, there's only 3 bonds and no lone pairs around boron. So it doesn't have a full octet. It only has 6 things around it. So there's space to accept another bond, right? Okay, tell your neighbor how the arrows are going to go. You start with the lone pairs. And put the lone pairs where they're going to form a bond to the boron. Okay, if nitrogen is neutral, when it donates a lone pair, it's going to have a positive formal charge. If boron was neutral, when it accepts a bond, it's going to be negative. So you end up with that product. Back to the screen. So remember we talked about metal chelation processes? I introduced coordinate covalent bonds to you. Okay. Reaction is this. Call it a metal chelation reaction. But if you notice, all of the ligands have a lone pair. And those lone pairs on the ligands get inserted into an empty orbital on the metal cation. So that's a Lewis acid base reaction, where the metal cations are Lewis acids and the ligands are Lewis bases. You're all walking around breathing air because of a Lewis base reaction, Lewis acid base reaction. So heme without the iron in it, these are lone pairs. And the iron inserts itself in heme that's part of hemoglobin because of a metal chelation or a recessive-base reaction where the lone pairs get donated to the iron. Okay. Spend the last 10 minutes working through recitation. And get questions.